Thanks, Richard, and thanks for giving us the opportunity to present on behalf of our team. Our purpose as a project is to produce useful, usable technology to help farmers make better soil decisions. And our emphasis is really on that useful and usable. The agtech space is full of gadgets, toys and widgets that don't add value, that can actually make life harder for farmers. We want things that are farm-proof, usable. The three products that we're developing in this project is the Smart Shovel, which is sort of no longer a shovel, more like a probe. The BILBY, which is a form of below-ground communications, and the self-learning sensors. And I'll just run through them each briefly. So the Smart Shovel fork concept, the concept came to me from growers who kept saying, I've given up using soil moisture probes and I've gone back to using a shovel to work out if I need to irrigate. So let's build them a smarter shovel. And we've gone through many iterations and we're now looking at something that's rather probe-like. And what we're trying to do here is something that's quite unique, that there's no other tool on the market that can do. And that is to simultaneously measure soil moisture, penetration resistance or compaction, temperature, salinity and apparent conductivity as it's being pushed through the soil in real time. And for that to be displayed on the device and sent to a phone and mapped automatically. Okay? And it's quite a difficult task. We're having to develop new theory to do it. The issue is that most soil sensors look like the one on the left. They look like an antenna, and they are an antenna, and we've broken that design. And by breaking that design, we're having to go back to very first principles on how it behaves as an antenna in the soil. And so we've spent almost a year and a half in the design and calibration of the sensor tip at this point, and we're still not finished. It's a very complex job, but we're actually making very real progress. Here's some data that we got last week, comparing our probe in orange to a TDR to a Hydra probe. And those different bits, if you like, are different temperature regimes. And you can see our data, the orange, is a lot more stable than the other commercial devices, and it doesn't vary with temperature anything like the other devices. So we believe we're going to have a device that's as good, if not better, than the best that's on the market now. Okay? And we've developed all these calibration type chambers to do all this work, and they're all automated. Okay, and yesterday we produced and showed our first prototype of the device to our farmer group, and this is Simon, our lead engineer, and what he did to the hotel room to get to that point. We also have some really excellent work by USQ in developing a mobile phone app to go with the probe, so it's not just a device that connects, and it's got this additional ability to generate heat maps and actually trig and map between samples, lead you back to where you took a sample for resampling and other functionality. The second device is the BILBY. The BILBY is a below-ground wireless communication node. It's not a sensor. What it does is send sensor data to the cloud via communicating through the soil. So at the moment, if you want to drop a soil moisture probe into a paddock, you need a solar panel, a data port and a modem, which all sit above ground. And that's a problem, because if the cows don't eat it, you run over it with the tractor, and if the tractor doesn't get it, the cockatoos get it. So our technology is going to allow growers to measure soil moisture and other soil sensors in places where they can't currently measure these things, and most importantly right in the middle of paddocks, right in the middle of crops. And so it sends data through the soil. And the plan is a 7-year battery life, and tests so far have shown we can send data up to 1 kilometre from a node that's buried at 30 centimetres in the ground. Okay, sorry, wrong one. And just to emphasise, the BILBY is a component in a system. It replaces that above ground component. So we've built it to be highly adaptable with almost any soil moisture sensor and compatible with almost any gateway. And so it just replaces a component. We've done quite a bit of field testing so far. We designed 5 different antennas and tested them and came up with our selected one. We've basically rethought an antenna for soil. It's been a key breakthrough. We've done field trials on 3 different soils around Tasmania, and we're about to have a whole farm trial of 20 nodes, 20 bilbies with 5 gateways, and we're going to sequentially crash the gateways to test connectivity in worst possible scenario conditions. And here's some of our data from Campbelltown showing the signal strength by distance for our different antenna designs. Okay. Our third product is the notion of self-learning soil moisture sensors. So, sensors are stupid. Sensors don't know what soil they're installed in. They don't know why they're sensing. They don't, they're a very simple device in many ways. And what if we could use the sensor data to learn about the soil and the environment and the farming system in which that sensor is installed? And so we're looking at the use of AI and machine learning to go from this, a soil moisture monitoring from a probe, to actually determining the soil water retention function. And this is actually the pore size distribution of a soil. So it sets the limits for irrigation, your available water, readily available water. It converts soil moisture to matrix potential. And it's also a map of soil macroporosity and soil structure and function. That physical sense of soil health is mapped here. And we have a very brilliant student, Shenting Shentingi here. She'll be hiding now, feeling embarrassed. Now, Shenting, she's the person who's leading this research for us. It's not simple, but this is the idea, is we go from a moisture probe with sensors every 10 centimetres generating soil moisture data on a daily basis. Our model sits in here, our very clever AI system. We generate a profile in which we've got water moving up and down the profile. And you imagine Hydrus 1D as the type of model we're talking about. And what it does is it tweaks the 5 Van Genukten parameters as you're going until the model is predicting soil moisture exactly the same as our soil moisture probes. But that only gets us so far because most of the soil moisture is in very wet zones, so it's going to be looking at whether we can couple it with neural networks and pedotransfer functions to also get the dry end of the retention curve. So there's a whole range of ways that we're actually looking at it in terms of the model development and the AI. And we've got 3 field sites set up at the moment. They've got probes and weather stations. We're going to be setting up at least 2 more. In which we're going to be measuring the soil water retention properties in very close detail using lab procedures so that what we solve we can compare back to laboratory measurements as well. So very finely calibrated and compared. It's quite common in these digital studies that there's never actually a true measure. It's just whether the model converges. What is truth becomes a difficult question. And Shenting's progress has been very substantial. She's developed code for Richard's equation into the model, this Kalman filter which does a lot of the AI type stuff and data washing, and she's still got a lot of work to go. Okay. And I'd just like to recognise that the success and the progress we've had with the project is due to a very large project team from different entities within UTAS and other universities, particularly Federation and USQ, and our grower groups who have been really, really important in guiding how we develop technology and ensuring that it's usable and useful, being our honest broker for us. So thank you guys.